Today, we will be discussing fraud in the financial services sector, and we will demonstrate how, by combining the power of TigerGraph software and AMD hardware, we can catch more fraud more effectively and more efficiently than ever before. My name is Dermot Smith, and I'm a sales engineer with TigerGraph, and I'll be doing the presentation today with Kester Arnott, who is a field application engineer with AMD Xilinx. But first, a bit of context. So, fraud software currently doesn't stop enough fraud. So the annual spend on fraud detection software is about $2 billion. But the losses related to fraud in the financial services sector alone is about $50 billion. So clearly, there's room for improvement. And typically, the way the fraud detection is done is by using machine learning models. And so what they do is they take some existing data points, put them into the model, and then the model is then used to detect fraud. But after a certain point, you can only squeeze so much improvement using what you have. And so by tuning the machine learning algorithms bit by bit, gives you diminishing returns. But actually, the problem is not the algorithms themselves, but it's the data that you put into them. So your data is naturally made up of data points and the relationships between those data points. The existing machine learning models approach, they just take the raw data points, put them into the model, and are then used to detect whether something is fraudulent or not. But if you don't capture the relationship between those data points, you're effectively throwing away half the information. And so this is where TigerGraph and graph features can help in the detection of fraud. Because by incorporating the relationships between these data points, we can give new information to a machine learning model and get better results. And so just to imagine this a bit more visually. So a typical machine learning feature set consists of data points. And so that data points might have name, age, when the account was opened, transactions, things like that. But these data points, they live in isolation, and the relationship between those data points is not captured. However, by taking the data and putting it into a graph database like TigerGraph, we can effectively model the relationships between those data points and capture things like payment flows, relationships between people, and also shared characteristics. And this information then can be incorporated into the machine learning model to make it more effective. An example of what we call a graph feature that can be incorporated into a machine learning model is a concept of centrality, i.e. how important a particular data point or node is in the overall network. So for example, this could be an account that receives an abnormally high number of inbound and outbound transactions. It could be a person that has lots of accounts, etc. And so one of the algorithms that we have that can be used to assign a score to the relative centrality of this data point is an algorithm called PageRank. And so by using this algorithm, we can see how connected and how influential a particular data point is, and then that can be incorporated into the machine learning algorithm. Similarly, another feature that we can add, another graph feature, is the concept of community. And so typically what we've seen is that, say, fraudulent activity typically have data points that are linked together. So for example, maybe one particular account is linked to another account 2 or 3 transactions away. Maybe the fraudulent activity occurs in a particular location, etc. And with that, an algorithm that captures this community, it's called a Louvain community detection algorithm. It can run across a generic graph in order to group data points into natural communities. And then this graph feature can then be incorporated into an existing machine learning model to improve the performance. And what we've seen is that top banks that have used these graph features, they get a significant boost in fraud detection rates. And the way this would work is that you would have, say, your existing approach where you would have your core systems, maybe it goes into a data lake, and you have your existing ML feature generation going into your fraud detection application, and that gives, say, result X. But if you incorporate what we discussed, the TigerGraph graph database with some graph features as additional features into this machine learning model, we've seen that, for example, one bank reported a 20% increase in fraud detection. And in addition to which, it's something that gives a very good return on investment. So it's a type of application that's easy to implement, easy to incorporate, and easy to get the return on investment very quickly. And why should you use TigerGraph for this? Well, basically, we can traverse data deeper and expose the relationships that are much deeper than, say, other platforms. We're faster, 5 times faster, and we can scale. And these are the reasons why our clients have chosen us over some other of our competitors or other approaches. So that's enough talking. What I'm going to demonstrate is an application that was built using TigerGraph to detect application loan fraud. And so this is actually TigerGraph itself. And so what we can see here is that there's a loan application that's linked to an address. That address is found in a particular zip code. This application is applied for as this person. This person was born in a particular year. There's a phone number associated with the application and an email address and an email provider associated with that email address. And in addition to which, in order to facilitate the training of the machine learning algorithm, we created what we call a feature set vertex, which incorporates all of these data points associated with this application into a single vertex to make it easier to actually exploit inside of a machine learning model. Now, in terms of what this data actually looks like, so what we can see here is that this application is associated with a phone number, email address, identity, etc. But this phone number is also used by another application. And then this application is associated with a different person and with an email address, and this email address is associated with further applications. In addition to which, we can explore a bit more and see that this person has also tried to apply for other applications. And this is the type of relationship data, relationships between the data points that we can capture using TigerGraph and import into our machine learning model. In addition to which, we can also have an idea of community. So we can see, once we run our community detection algorithm, we can group the data points into different communities and see the relationship between those data points. Now, in terms of what the actual machine learning model looks like and how you can incorporate these graph features, what we're going to do is we're going to load a feature data set, and we're going to initially load just the fraudulent applications. And so we can see that out of 10 million loan applications, the number of fraudulent applications is about 48,000, 49,000. And what we can do as well is load the non-fraudulent applications, except we're going to limit it to the same number of fraudulent applications so that we have a balanced data set. And so that makes it easier to train this algorithm just for the purposes of demonstration. And so we can see here that our combined data set is around 97,000 data points. And what this actually looks like is we have channels, which is the channel on which the application came in on, birth year, zip code, a numeric representation of the email provider, and the first digit associated with the loan amount and the last digit. And so these are what we would call non-graph features. So they're just kind of standard features that can be used inside of a machine learning model. And what we've added is the community ID, which is the Louvain community detection, and also PageRank, which gives a score assigning the relative importance of that node inside the actual graph relative to other nodes. And so what we're going to do here is we're going to use these graph features, use non-graph features to train a model, and then use those non-graph features combined with these two graph features to train the model. And so what we actually see is that when we train the model, so we have some metrics associated with the performance of the model. That's a confusion matrix. It's kind of a standard way of measuring, visualizing the performance. But what's important to examine here is the relative feature importance without using graph features. So we can see here that the email provider and the zip code are the two most important elements when determining whether an application is fraudulent or not. Now, if we look at, if you do the same thing, except we incorporate graph features, we can see already that the performance of the model has gone up. In addition to which, we can see that by using incorporating the graph features such as PageRank and community, we can see that those two graph features have become much more important in determining whether this loan application is fraudulent or not in terms of the overall performance of the model. And so if we just compare that, so we can see here that without graph features, the Gini, the area under the AUC and the AUC PR, without the graph features, they're not too bad, but we can see that with the graph features incorporated, there's been a significant improvement in the overall performance of the algorithm. And so when I talk about performance, that's the ability of the actual model to differentiate between fraudulent and non-fraudulent applications. And so if just for context, it's using the XGBoost model, and by incorporating graph features, we've seen a significant improvement in the performance. In addition to which, if we look at the precision, so the precision is a measure of the accuracy of the quality of the model, i.e. how many of the things that were flagged as fraudulent were actually fraudulent. And we can see already just with that, there was a 35% increase in the precision of the model. And the last one is a measure of what is recall, which is a measure of quantity. So how many of the real frauds out of the total amount of frauds were actually captured. And so we can see there was a slight decrease when we incorporated graph features. But it's important to note that there's actually a trade-off between precision and recall, or the accuracy and the quantity. So for example, you could have perfect precision in that you flagged one. Imagine that in the data set there was, say, 100 fraudulent applications. And so you flagged one, and yes, that one was a fraudulent application. So you could have a precision of 100, but you miss 99 other applications, fraudulent applications. So that's not actually a really good model. So similarly with recall, we could have great recall, as in we could catch out of the 100, we could catch 100. But if we also flag another 9,000 or so other applications as being fraudulent when they're not, that's a really poor performing model. And so we can see here that by incorporating the graph features, it's a fair trade-off between a massive increase in precision versus a slight decrease in recall, and to produce an overall much more effective model. And so how does the AMD hardware help us? So AMD have an FPGA card which can be used to accelerate some of the graph features or the graph algorithms that TigerGraph uses in fraud detection. So for example, when we ran the Louvain community detection algorithm against the entire data set, which is about 500 million data points for 10 million loan applications, we can see that when we ran it once with using TigerGraph, pure TigerGraph with CPU, and another one using the FPGA that's integrated with TigerGraph from AMD. And we can see that if we look at the comparison here, we see that with TigerGraph, pure TigerGraph and CPU, it took around 2 minutes and 23 seconds, whereas using the FPGA card from AMD, it took only 41 seconds, which is an improvement of almost 250%. And similarly, we can see that the amount of memory that was used when we used the FPGA card was also decreased by about 20%. And so what I'm going to do now is I'm going to hand over to Kester, who can talk in more detail about the advantages that the AMD Alveo FPGA card can bring when used with TigerGraph.
Thanks, Dermot. So if you can bring up the presentation again.
Yep.
So what Dermot was showing in the demo was the Louvain modularity detection, which was accelerated on our Alveo cards Now, this was with a limited data set. If we look at proof of concepts we've done with customers on huge data sets, their own data sets, we see an even better improvement. We see up to 45x runtime improvement and a lot less memory requirements on the host. So on real data sets, the system actually performs even better using the Alveo acceleration. Similarly, we've implemented on our accelerator cards different algorithms, which can also be integrated into TigerGraph. We're still working on others, but the initial proof of concepts we've done all show a significant improvement in performance, while either keeping the memory requirements the same or reducing the memory requirements. So if we go to the next slide, we can have a more detailed look at what card makes this possible. So this is the Alveo U55C card, which is a PCIe accelerator card, which has an FPGA, field programmable gate array on it. That FPGA has 16 GB of memory, which is very high bandwidth memory, which can be directly accessed from the accelerator cores running inside the FPGA. Now, the nature of an FPGA, the architecture of an FPGA is basically a huge array of logic cells which can perform any function that you program to it, with a lot of routing to have your data transported over the whole device. And then it has dedicated memory embedded in the device and dedicated TSP blocks to accelerate multiplications, additions, accumulations, and so on. So all of these combined allow you to efficiently implement your algorithms on these cards, on these accelerator cards. So a bit more detail on that if we go to the next slide. A typical implementation of a complex algorithm on FPGA would rely heavily on using function level pipelining. Pipelining not only improves the throughput tremendously, but also reduces the strain on the memory because data is streamed within the device itself and doesn't have to be written and read from memory continuously. So that both improves performance significantly and again reduces the memory bandwidth requirements as a whole. Another big advantage of using accelerator card is the fact that these cards have 100 gig Ethernet interfaces, 2 of them per board, which allow you to do a scale out very easily without requiring any CPU cycles for implementing a TCP IP stack to transfer data throughout the network. So we can transfer data directly from one U55C to other U55Cs independently of a host CPU. That reduces stress on the CPU while having a high bandwidth, high throughput network scale out. Because of the nature of an FPGA, data pipelines with arbitrary widths are actually very easy to implement. So you can implement a specific algorithm tuned to your application very efficiently without wasting any resources. And on top of that, because of the highly parallel nature, you can very easily use multiple blocks in parallel, which give you enormous throughput, which allows you to achieve the required performance or run as fast as possible, basically. And then, as I mentioned, this card has 16 gigabytes of HBM memory on board, which allows your algorithms implemented on that device to benefit from that huge bandwidth you get from to access your DDR interface components. So all of this combined, the huge bandwidth to memory, the efficient implementation, the parallel architecture of an FPGA allows you to accelerate these high performance compute algorithms very efficiently and offloading your host CPU from the hard work of running these complex algorithms. With that, I want to thank you for your time. I hope you learned something, and I hope to talk to you soon.